I have generated a Fourier series approximation to a triangular wave using three terms. So these are the three terms here: 8 upon pi squared sine 2x minus 8 upon 9 pi squared sine 6x plus 8 upon 25 pi squared sine 10x. I've rewritten this as a polynomial, and I've put the polynomial into a graphical calculator. Now in white you see the ideal triangular wave that we expect to get, and in the green here we see the actual triangular wave that we're going to get through the Fourier series approximation with three terms. Now I've split the values here for our triangular wave into 0.1 radian segments. So this point here is at 0.1 and this is 0.2 and so on and so forth. Now what we're going to do is we're going to take our Fourier series approximation with the three terms and we're going to code it into our assembly language, run it on our machine, and then we're going to get the actual simulated points, and then we will plot the simulated points on top of the points in blue. So let's go ahead and do that now. We have two pieces of code. On the left hand side we have the actual subroutine for the Fourier series. On the right hand side we have the calling function for that subroutine. So let's look at the actual subroutine first. We're going to have the first term here, which is generated by this section, and the second term, which is generated by this section here, and finally the third term generated here. Whenever we add all of them together, we return the value that is the final answer to the calling function. So let's see the calling function. In this we're going to pass in 64 values. Each of them are going to be separated by 0.1 radians. So we have the value here x, and it's a fixed point 0.0, 0.1, 0.2, 0.3 and so on and so forth. So these are the values which are passed into the subroutine called Fourier. Now whenever it's worked out that Fourier value, it passes the answer back out into this Fourier underscore x. So let's load it into the machine and let's see it running. I have loaded the Fourier series subroutine into the ROM, so let's go ahead and we will load the calling function into the RAM. So that's the calling function all loaded in. Now let's run the simulation. So we can see the simulation is now running, and if we drop in we can see that the ROM is being accessed and also the RAM is being accessed. And if we drop into the actual CPU and the control unit, you can see all the sets and enables for all of the registers being pulsed via the microcoded ROM. So I will run this simulation until it's finished, and then we will go in and have a look at the final results. Now that's the simulation finished, so let's drop in to the RAM and we will see the final results. So you can see here that we have the initial input values here, and that goes all the way up to the endpoint FF, and then the results start from this position here all the way along to the final position here, 0005. So let's take these values here, which are in our fixed point, and we will convert them into decimal and then plot them back onto the graphical calculator. Now the expected values you can see here in blue. So let's superimpose the simulated values from the CPU here in pink. And as you see, we have a very good approximation to our triangular wave. So let's zoom in and we'll have a look at some of the individual points. And as you see here, the expected value here is this value 0.4961. In this instance here, the actual value we get from the simulation is 0.492. So you can see here that we do have a very good approximation to our triangular function. So I'm very pleased at the accuracy of the CPU and the accuracy of the assembly language coding. So thank you for listening. I'll get you on the next video. Goodbye.